recording. So as I was saying, Dr. Poon is also affiliated faculty at University of Washington Medical School, and Dr. Poon is really a true pioneer in AI for healthcare, leading many groundbreaking research in biomedical NLP, precision health, and his team has developed many influential open source models. I bet you have probably used, definitely read about, such as PubMed BERT, a language model for biomedical literature analysis, BioGPT is generative model for biomedical text related analysis and tasks, and Biomed Clip, and that can link biomedical text to images, and LavaMed, and this can process biomedical text and images together. And recently, GigaPath analyzing digital pathology images at scale. So his team has been pushing the boundary of large language model and multimodal AI in medical applications. And he has a PhD in computer science from University of Washington, has many numerous accolades from top AI conferences. And Dr. Poon brings a true expertise in both machine learning, NLP, and their transformative potential in healthcare. So without further ado, let's welcome Dr. Poon to share his insight about AI in healthcare.
Yeah, thanks so much, Jimeng. So really appreciate the very, very kind introduction. I'm actually a big fan of all your works and in the AI and biomed space. So really looking forward to learn from all of you and maybe even explore some synergy and collaboration down the road. So by the way, can everyone see the slide, the full screen slide?
Yes, you can see.
Okay, awesome. Yeah, so as Jimeng mentioned, I've been in Microsoft research for over a decade and basically trying to see if we can sort of help advance AI to accelerate progress in precision health. So here basically just try to, I mean, we have over the years gathered lots of battle scars and some learnings. So really want to share some of the lessons we learned and some of the latest progress. And again, we really love to kind of pick you guys' brain and explore potential synergy. So first, let me, can you guys see the slides advancing?
Yes.
Awesome. So I will start with kind of motivated a little bit of precision health, which many of you probably familiar with already. And this really sort of like motivated a lot of our overarching agenda in basically trying to learn patient embedding that encapsulate the multimodal longitudinal information for our patient, right? And now the very exciting kind of like progress in generative AI obviously kind of like really add a lot of fuel to this progress, right? So, but certainly there were hypes and so forth. So I will give a very quick overview to see, hey, where are the places where actually Gen AI are already making a fundamental, change, right? So where are the places where there is a prominent growth area? Now, one of the big growth opportunity is actually when you go beyond text, right? So when you look into the multimodal space. So one challenge is that there are many of this kind of new modality like digital pathology, for example. Actually, a lot of the general domain, AI doesn't work very well there. So I will using digital pathology as an example, as Jimeng mentioned, that to like report some of our recent work in GigaPath as a kind of example how some of those competency gap can be bridged. But more importantly is that even if you figure out how to read CT, MRI, digital pathology, but how do we combine each of them together, right? So that actually lead to sort of the ultimate challenge of multimodal reasoning. And I will highlight basically a research hypothesis of kind of using the text modality as an interlingua to essentially grounding all those modality and reason with that. And lava mat, as Jimeng mentioned, being sort of a one example recipe, how we might be able to do that. And then I will conclude with some real world applications. I would love for this talk to be more interactive. So please feel free to interrupt me anytime. And I will lean on you, Jimeng, to look at if there are questions and chats and so forth, right? So feel free to interrupt me anytime. So obviously, like in the ideal world, right, we really want to the each patient to be able to respond to the treatment they have been prescribed. So as signified by the blue person on the left here, right? So and unfortunately, in the real world, many patients don't respond to the treatment, right? So as signified by the red person here, this is obviously a huge waste and unnecessary sufferings and so forth, but also a giant miss of treatment opportunities, right? So cancer is really the poster child for this challenge and opportunities, right? So many of you know cancer have been through several generations, right? From early days slash poison and burn, kill every dividing cells, right? To basically the targeted therapies and so forth, right? The challenge has always been that cancer is very robust. It has the blessing of natural selection. So it always figure out some of the mutation and then circumvent the treatment and then come back, right? So that leads to the latest kind of like cutting edge immunotherapy, and by essentially mobilizing immune system, right, to fight the cancer. And immune system is actually the one health system that has the blessing of natural selection as well. It's actually designed to deal with a lot of the mutation, right? So you can think about COVID as a prime example, even though COVID still keep mutating like crazy, right? But after initial exposure, either through vaccine or natural infection, um, the immune system are perfectly capable of start handling a lot of the future mutations, right? So in cancer, specifically, you see some of this big progress, like the blockbuster drug like Keytruda, right? That actually can work miracle on some of the late stage cancer where nothing else, right? Now, still, this is very promising, but still, like if you look at overall the response rate for even some of the best drug like Keytruda, right? The response rate is still hovering around 20-30%, right? So that's far, far away from being done, right? So ideally, the dream is that if we can have this continuous learning health system, right, to keep monitoring who have using this new drug, right, which one work, which doesn't work, right, then if we can instantly incorporate those into the health system, then we can drastically sort of like optimizing care delivery and accelerate biomedical discovery, right? So one of the key underpinning about this direction is something called real world evidence, right? So the whole idea is actually very simple. It's like every day, if you look at what's happened going on in the hospitals, right? There has been billions and billions of data points collected that document the patient journey, right, from diagnosis to treatment to outcome, right? At the beginning of each journey, right? So even the best doctor may not know what will exactly happen to the patient. So each patient journey is almost like a mini trial, right? And then each encounter actually add a lot of the new information, right? But today, unfortunately, if you look at the bulk of this data, they have been using for diagnostic, they have been using for billing, right? But then afterwards, it basically get locked up in the attic and gathering dust, right? So here the holy grail is that can we leveraging the latest progress of AI, unlocking all this insight, right? And that can become essentially a population scale free lunch, right? So if we look at the broader scheme of things, right? So I mean, Jimeng, you guys have also done a lot of great work, like for example, in clinical trials and so forth, right? So there are actually a lot of kind of different stakeholders in the whole health system, right? So other than just doctors, right, and providers, right? In particular, a lot of the, for example, drug developers, clinical researchers, they really hungry for a lot of this kind of insight to accelerate discovery, to do clinical trial matching, right? Like you guys do post-market surveillance and so forth. And also there are payers who really need those insights to guide value-based care, regulator need the evidence to approve drugs and so forth, right? So, and obviously everybody, there are lots of people who recognize the importance for the real world evidence, but in the past, like the AI are just not very good, right? So then people are just limited to, for example, structured data and so forth. So very rarely touching on all those kind of additional modalities and so forth. But now for the first time ever, we can start to imagine that the AI could be sufficiently good that we can start to unlock sufficient high value insight, right, that to justify creating such a platform, right? So specifically, if you think about sort of like what are buried inside those real world data, right? So here's a DID journey of a cancer patient, right? Very typical cancer patient. So each bar is actually one clinical note, right? So you see there are many different node types, and also each node actually capture a lot of information about the cancer patient, right? Now, in addition to the nodes, there are also lots of kind of like information-rich modalities, right? That, for example, cancer patients start with, usually you have non-invasive stuff like CT, MRIs, and so forth. Then you got biopsy and resection, then you start to get digital pathology, genomics, and so forth. And nowadays, there are also fancy stuff like single cells and other measurements, right? So each of this modality is basically trying to tell you something about the cancer patient, right? And each of them give you very important information, but still very limited, right? So only by putting all those information, assimilating all those information together, we can recapitulate the holistic picture about the patient, right? So in a nutshell, you can then think about precision health, right? From a sort of a computer science point of view, a nerdy way to think about precision health is basically you try to say, okay, I was trying to learn a function, right? That's starting from multimodal input, right? And then I'm trying to predict, what happened to the patient next, right? So for example, how would the cancer progress, right? Would the cancer recur, right? So the disease progression, but also would the patient respond to the treatment, right? And if we can actually predict those kind of medical events sufficiently accurately, right, then we will be getting very close to the ultimate dream of precision health, right? Now, of course, this is much easier said than be done, right? So first of all, it's not just a snapshot that matters. It's actually a whole longitudinal journey for the patient that's really important, right? We need to actually synthesize all those longitudinal information. And also, unfortunately, most of those actually information could be missing, right? And they could be missing non-random, right? So that's sort of like ultimately that's the challenge that we're facing in precision health. And but that's also where actually we can potentially harness the latest progress in generative AI, right? So the generative part is basically referred to a generative model, right? And the beauty for a generative model, the superpower there is that it can conditioning on what are observable, right? It can try to predict the basically the latent, the non-observable, right? So we can obviously using that to start inferring all the missing stuff, right? We can also intentionally hide some of the observable stuff and then using that to be the self-supervision to train the generative model, right? And then if we are kind of like do really well, then the prediction task we talk about is just a special case, right? And so in a nutshell, basically what we want to do is that starting from the population level real world data, right? Can we portray a powerful biomedical foundation models, right? So, and the GenAI disruption means that for the first time ever, we can potentially learn a very high fidelity patient embedding, right? That essentially almost can serve as a digital twin for the patient, right? To start to kind of like capture a lot of the evolution of the patient journey, right? And if you have such a high fidelity digital twin patient embedding, then you can start to do patient like me reasoning at the population scale, right? So these days with cancer patient, people tend to be, okay, let's go ask for second opinion, third opinion, right? Now, with this kind of patient embedding, you could actually basically do, 5 million opinion all at once, right? You can snap your finger, find the patient like me, most similar patient, right? And then you can interrogate what happened to them, right? So which treatment have been used, which work, which doesn't work. So that information can immediately help improve patient care, right? But you can also start to figure out who are the exception responder, who are the non-responder, and then you can start to say why are they different, right? How are they different, and can I stratify them better, right? That can lead to better companion diagnosis, but that can also potentially unveil some of the mechanisms, right? Underlying the differences, right? So many of you probably super familiar with the concept of emergent capability, right? So if you have a high enough capacity models, right, and then have feed it with a large enough amount of data, right, then it can start to acquire some competency that you don't even expect at the beginning, right? So here, the really interesting big picture thinking is like, if you think about imagining tomorrow, right, you have GPT next, right? Actually literally read every single literature, every single medical guidelines and so forth. Is that sufficient, right? Arguably, that model can capture the current healthcare common sense, right? But as we all know, right, today's medicine, as we show at the beginning, today's medicine is very limited, right? It's very imprecise, right? If you look back 200 years, right, you look at how medicine was practiced at that time, right? You will say, oh my God, that's so barbaric and primitive, right? If we go forward to 20 years, right? And look back at today, we might also feel like, hey, today we many places we don't know what we do, right? So here the potential superpower for actually doing this population scale learning is that we may be able to actually uncover a lot of stuff, right, that are already discernible from the data, but right now actually is not aware by today even the best doctors, right? So those are the kind of emerging capability that can help drastically move, transform the medicine and move it forward much faster, all right, than today's kind of like slow pace. So anyway, so that's sort of like kind of the bigger picture. And the question then is like, what are actually in the generative AI revolution that actually can already be helpful, and where are the growth areas, right? So, um, um, I'll show you some example about sort of what I would loosely call universal structuring or universal abstraction, right? So basically, it's like in the past, when you do information extraction, you probably have to train individual models and so forth, right? Now, actually, with some of the frontier model like GPT-4, basically out of the box with some prompt engineering, you can actually easily do a lot of the long tail extraction, right? So with very minimal efforts, right? So that will have a major implication because a lot of those information currently are buried inside those unstructured nodes, right? You can also using it to not just translate literally at languages, but you can also translate between ontologies like OMOPs and FHIRs and so forth. That can have major implication on interoperability, right? You can also you can treat, for example, a GPT-4 instance as basically reasonably smart, right? Reasonably knowledgeable kind of assistant, right? That can understand a lot about, instructions and biomedical jargons and so forth, right? So you can actually using it to follow instruction to maybe start to annotate data and so forth. So that can have major implication on scaling. How do you create data set? How do you create evaluation systems and so forth? And ultimately, you don't want to trust any of this frontier model for the veracity of facts, right? Because sometimes they could hallucinate, they could mix up, they don't know things and so forth. But they are definitely very, very powerful reasons. So, and one of the very kind of like close imminent future is that you could harnessing the reasoning capability, right, to start being able to talk to the data and make sense of it, right? So that's really sort of the super, super powerful capabilities. So all of this basically are what generative AI currently can already do, especially on the text modality, right? So for example, many of you probably familiar with the MapProm work. It's really just a 2-week hackathon that we did at Microsoft Research. We basically want to ask ourselves like, hey, what if we don't want to fine tune any of the model? What if we don't want to change any of the weight, right? How best can we do in, for example, USMLE exams, right? And the MathQA tasks in general. It turns out you can do surprisingly well, right? So this is the first time we show that basically a model out of the box and can get 90% above, right? So, but moreover, it can also do very well on a whole slew of biomedical NLP tests, right? So all in all, you can say that in biomedical text front, right? This frontier model are actually very proficient, right? And it's not hard to understand why, right? Because like if you go to the public web, right, there are 30 million PubMed papers, as Jima mentioned, right? And then you obviously all this model have read, all the WebMD like pages, right? Have maybe read all the transcription of the biomedical podcast and so forth. So it's very, very good at understanding biomedical text and reason about it, right? So for example, if you think about like clinical trial, right, matching the problem matching trial with patient, right? So one of the bottleneck is like how do we interpret those eligibility criteria, right? So some of you have done amazing work there, so I wouldn't belabor you guys what it is, right? So one of the really amazing thing about GPT-4 is that you can basically write a very natural, intuitive instruction, right? It can actually parse all those elaborate matching logic for you directly, right? So, and then on the flip side of that, right? So this is about understanding the trial criteria, right? On the flip side, you can also using GPT-4 to figure out what's happening with the patient, right? Which is important for the matching, right? So here I want to highlight one particular exciting prospect, which is like obviously for simple stuff like maybe health status, biomarkers, and so forth, even regular expression can do really well, right? But actually what the amazing thing about this frontier model is that even for very elaborate stuff, right, that require understanding a lot of bits and pieces and also following the guideline and piece them together, like for things like clinical staging, right? So some of you might have read AJCC, right? A 600-page book, right? So for each cancer type, they specify a lot of detail, like how you would look for individual piece of evidence for the cancer, and then you piece them together to determine what's the stage, right? And amazingly, you can pretty much ask the model to read the freaking menu, right? So to say, let me put the instruction in the prompt, and then let me put the notes there, and then the model can essentially follow the instruction, right, in an 80-20 way. And oftentimes it's actually do comparable even to the best, first generation frontier model, sometimes even better, right? So what this means is that in the past, for every single data element, like especially the complex stuff like this, right, you probably have to train your individual models, and that could take months, right? And now it could probably take days, right? So that's super exciting on the text front. But Gen AI also have some very salient competency gap, right? So whenever you go beyond text, that's when you start to expose some of these major limitation, right? For example, like if you ask them to say, hey, can you draw me a lung CT scan, right? Oftentimes they will draw you a glowing lung, right? So in general, the problem here is that if you look at the public web, right, it does have lots and lots of biomedical text, right? But on the other hand, if you think about multimodal longitudinal patient data, right, typically you don't have a lot of that in the public, right? So which means that actually frontier model have no idea about it, right? So that basically brings us to the challenge facing us to kind of like advancing towards a precision health, right? Is that how do we deal with all this multimodal complexity, right? So the first big challenge here is that for many of those modalities, right? If you look at like 3D CT, if you look at digital pathology, if you look at MRIs and so forth, right? You really don't have very comparable general domain kind of like AI that actually can immediately plug and play there, right? Because they exhibit very, very different characteristics. So in a couple of slides, I will show you one concrete example in digital pathology that really illustrates this problem. So individual modality, there are lots of challenges. Moreover, there is also a big challenge is like even if you have some good handle on individual modality, right? How do you
How do
piece
you
them
piece them
together
together?
to there seem to be some open mic, so and anyway, so you can, and how do you actually piece them all those multimodal together, right? So basically in the remainder of talk, I will basically focus on these two aspects, right? So let me first show you sort of like one general recipe. How do you do modality specific cell supervision, right? So again, many of you actually have done amazing work here. So I would just report some of our latest finding in the digital pathology from our side, right? So first of all, you ask like, why do we care about digital pathology, right? So basically digital pathology is like when you get a tumor tissue sample, right? You cut them into very thin slice, right? And then you put them on very high resolution microscope, right? To see how does it look like, right? You put some special chemicals so that it can reveal the cellular structure, right? So you can see the nucleus, you can see the cytoplasms and so forth, right? And one of the key reasons why so-called H&E pathology slide are very important is that it basically, if you look at these images, it can tell you how the tumor microenvironment looks like, right? So specifically, it's like there are the tumor cells, right? So here signified by the melanoma, right? So this is a melanoma slide. So you can see the big arrow pointing to the melanoma cells, right? But there are also immune cells. So here, basically signified by the big L, right? So the lymphocyte, right? So turns out that actually the configuration, the global configuration of those cells would actually be very important for understanding the tumor microenvironment, right? So intuitively, you can think about like if there are already a lot of immune cells deeply penetrating the tumor, that's actually a very good sign, right? So that means the immune system already know there is something wrong going on there. And then the immunotherapy basically work by stimulating the immune system, right? So you already know there is something wrong somewhere in the tumor, and now you mobilize the immune system and it will wipe out the tumor, right? Now, on the other hand, if immune cell doesn't penetrate into the tumor but only stay on the surface, that's a very bad sign, right? Because that means the immune system get fooled by the tumor, right? And it doesn't know where to go. Now, if you mobilize the immune system, it might even cause a so-called autoimmune overdrive and actually kill the patient before the cancer, right? So, so thereby, like understanding this global configuration is very important, and that's also why um, modeling the whole slide rather than small patches are very important, right? So in principle, we have the perfect tool like transformer, right? Essentially work by you have enable every pixel to send messages to every other pixel, right? So in this way, you can pretty much capture arbitrary complex pattern, no matter how complex, how global they are, right? But it obviously have a big Achilles heel, right? Because you have to pass messages between every pixel pairs. That means computation will be quadratic in the number of pixel or the input, right? And unfortunately, digital pathology slide are some of the humongous images in the world, right? So a standard slide could have 100,000, above 100,000 pixel on width and length, right? Basically, totally over billions of pixels, right? Some of my pathology colleagues told me with the following analogy, right? If you print them in standard printer resolution, right, it could take up a whole tennis court, right? So And also compared to web images, right, where your mean number of pixels could be just hundreds or thousands, right? A single pathology slide could be hundreds of thousands of times larger than the standard web images, which means that computational wise, a single slide could be billions of times larger than what you can typically process a web images, right? Using transformer, right? So then basically we face this big dilemma, right? So before our work here, most of the prior work basically then focused on the much smaller, what people call the patches or tile, right? So like for example, a 256 pixel times 256, right? So you focus on those much smaller tile, and then you just do some, rough aggregation, right, on top of that. But that's not very satisfying, right? Because go back to the early example, right? We really want to figure out arbitrary complex global pattern that even today, even the best pathologists may not know, right? So here the core idea is that we can actually scale transformer by doing the following. So at a very local scale, right? At a small kind of patch scale, right? You can afford to do full self-attention, right? So quadratic doesn't kill you, right? Because it's a very small size, right? Um, when you go to larger and larger segment, right? Eventually you go to the entire slide, right? That's when the quadratic start to kill you, right? But on the other hand, when you think about it, right? If in the local region, you already actually do sufficient message passing between the pixels, right? Then every single pixel actually already capture lots of information about the neighbors, right? Which means that when you go to the larger scale, right, then you can afford not to basically try to pass message across every single pixel pairs, right? In fact, that may be wasteful because you don't need to do that. Instead, you can pick some representative from each neighborhood, right? And then passing messages among the representative, right? So effectively, that mathematically, that transform into you introduce a sparsity in the attention, right? The sparsity will be proportional to the segment, right? So the larger the segment, the more sparse you allow them to pass messages, right? And then by making it proportional, you can perfectly cancel out the quadratic rule, right? So that's actually a really simple idea called dilated attention that originated in speech, right? Which also have this long context problem. And then we basically work with our collaborators in Providence and University of Washington. We actually adapted ideas into digital pathology, right? And frankly, actually, certainly the modeling is super exciting and so forth, but also as in any real world endeavor, right? Like getting all those data, processing them, figure out the computer infrastructure actually take 2 years before actually we do the modeling within a summer, right? So that's also a great example of how challenging in the real world applications are. But at the end of the day, we are super lucky we were able to pretrain the first kind of whole slide pathology foundation model over about 200K whole slide, consisting of over a billion image tiles, right? Our paper published in Nature a few months ago. I'm going to, in the interest of time, I'm going to skip some of the results, right? And suffice to say they're very promising, but feel free to ask me more questions about that. This is actually a dated slide. Just this morning, I find out that actually the monthly download in Hugging Face exceed 200,000. So super excited to see the community actually taking up. This is a worldwide web map showing. We are really surprised that we thought digital pathology is a little bit of a niche application right now, right? Because it hasn't, not every hospital have that digital pathology departments and so forth, but we actually find that even in Africa or some of the other developing region, people have been using our models and so forth. So very exciting. And in the grand scheme of things, right? So what GigaPath manifested is actually this general recipe to do more modality-specific cell supervision, right? So essentially, you can think about this as a generalized autoencoder fashion, right? So you can basically pretrain on very large amount of annotated images or other modality data, right? And then in the special case, like in the text modality, we already have very good models, right? And the encoder and decoder could be the same, right? So that's basically on the individual modality. But the hard question still is like, suppose we actually learn very good representation for individual modality, right? But each of them is almost like a distinct language, right? So for example, CT may be encoding tumor lesion in one way, right? In the embedding space, it will put tumor lesion somewhere, right? And whereas digital pathology will be mapping the same concept, maybe, but somewhere different, totally different, right? So now when you have basically all those modality trying to reason across them, then you run into a big language barrier, right? So that's actually very similar to what you happen in the translation, right? So there are hundreds, if not thousands, of languages in the world, right? So imagining having lots of folks across the globe, you want to actually learn everything about holistically what happened, right? But the language barrier basically, make it very difficult to exchange information, right? So in machine translation, obviously people figure out a way to get around this, right? So what they do is that they try to ground every language into a resource-rich language like English, right? So for example, if you have a language in Africa, you have a sub-language in India, right? There may be zero parallel data between them, but you can translate them through English, right? So first from African language to English, then to the sub-language in India, right? That's actually how commercial machine translation system work. That's how they scale to hundreds of languages and so forth, right? So you can do arbitrary translation among pairs in this way. So we basically want to accomplish this, but in the multimodal world for biomedicine, right? And we basically argue that text modality can serve as that interlingual, right? Because of for many reasons, right? So and we already have very powerful model for the text modality, right? It already captured lots of no human knowledge, right? And also, oftentimes for any modality under the sun, right? The study of that modality typically will leave some paper trail, right? Because we conducted the study often in natural language, right? So you're describing the data set, you're reporting the result, you specify the protocols and so forth. You have lots of text accompany any new modality, right? So that means like you could leverage those naturally co-occurring modality text pairs, right, to basically start grounding those modality, right? So here we basically build on top of the encoder and decoder, right, that we learn in the first stage, right, in the modality specific learning. And then we focusing on learning this lightweight adapter that is essentially translation layer, right? And to go from those individual modality to the text modality, right? So I will skip a bunch of kind of work. Basically, the biomed clip is about where are the public data for those, like for example, image and text pairs, right? So turns out there is a lot of them, right? And very excited to see a lot of follow-up work. And then I want to highlight, for example, a concrete example, which is the LavaMed, as Jimeng had mentioned. It's basically a general recipe. How we can actually do this is like, you can think about sort of like we basically using so-called late fusion, right? So all the encoder, decoder, those are modular, you can plug and play. And then we basically just focusing on learning that adapter layer, right? To translate from the image to the text modality. So it's basically using a biomedical image text pair to illustrate this general recipe, but you can also imagine generalize them to many other different modalities. And then another big important idea in the LavaMed represent is actually the idea of using the frontier model, right? Remember we talked about how You can use it as a universal annotator, right? So here's also a great example to that we using GPT-4 to essentially do create synthetic data, right? Again, in the interest of time, I will skip past the details, right? But certainly we can talk more if you're interested. We are barely scratching the surface, right? So even the best LLM model we released today, only using a tiny fraction of all the data we could have used, right? We are actually working on a LLM 2.0, very exciting progress that hopefully in a couple months we can show to you, all of you. We also then show that, okay, what if you can, we already show that you can do this with public data, right? But when you actually can get patient data, real world patient data, let's say radiology image and reports, right? Then you can actually, those are much higher quality and kind of like data, right? So we show that this actually can apply the same recipe to work very well. It actually outperformed GPT-4V by a lot, and even despite using a small model. And again, there is lots of exciting work afterwards. Super excited to see. You can also adjust the LlamaMap recipe by adding an image decoder, right? So now all of a sudden you can do counterfactual image generation. So one example is like imagine the following, right? If you have chest rate 6 months ago, right? And then you said, oh, what if the patient, right, have certain progression, right? How would the image look like, right? So that's basically a problem formulation in biomed journey. And then we show that in obviously a super baby step still, right? But we show that we can actually learn from patient journey, right? To learn such a counterfactual image generation model, right? And we can basically leverage readily available patient progression in their longitudinal record to train such a model, right? You can imagine then start using that to, do in silico imaging, to do generative diagnostic, right? To do virtual, imaging and so forth. So potentially open up lots of possible exciting things. You can also change the image decoder into a mass decoder, right? So then you can actually turning this into a unifying model, right? That you can identify the object, recognize the object, figure out where it is, right? Locating it, detecting it, and also outline the exact contour, right? So many of you probably familiar with SAM and MSAM and so forth, right? So here, what we actually enable in SAM, right? Their predominant way is that you have to specify a bounding box, right? And then you can start to do some of the segmentation. If you don't specify a bounding box, then oftentimes the segmentation result can be much worse. And here, what we actually try to harness is that in addition for the segmentation detail, we want to also learn object model, right? So we want to associate with the object types because that actually dictate how the segmentation looks like. Now, it turns out that if you do all this jointly, right, in a single model, then it actually help all the tasks, right? So it help recognition, detection, and segmentation, right? And then also the beauty is that, again, you're using text as interlingua, you're using text as a universal way to specify what kind of segmentation, what kind of object you want to find, right? So I skip some details, but we basically now already can handle 9 modalities across 82 object types. It's still far from enough, right? There are many more object types that our current model hasn't been able to handle, right? But this is sort of a pretty exciting kind of first step. And so I will kind of like just show you some kind of like future work, right? So obviously there are many other exciting modalities, right? So I don't have any time to talk about the agent framework, but that's a super exciting growth area, right? Another very exciting growth area is to figure out temporal time series modeling, right? And then we are fixating on this like tumor board scenario because it's a very good use case where you have radiologists, pathologists, genomicists, surgeons, and so forth gather together, try to figure out what's the best way to treat a cancer patient. How they do it today is completely not scalable, right? But imagining if we can have a multi-agent, multimodal system to scale the tumor board, right? So that can be a very exciting testing ground. So in general, after we learn a good patient embedding, we can also imagining, can we also learn embedding for everything else, right? For example, can we imagine learning embedding for intervention, right? And then anything like from diagnostic to patient care to discovery can basically become some sort of matching, right? So indeed, you can already show some success in the clinical trial space, right? So again, I wouldn't sort of belabor. I mean, Jimeng had even better motivation about this problem, right? So and the exciting prospect obviously is that can we do this 24/7 and so forth, right? So we collaborate with Providence, which is one of the large health system in the West Coast, and they start using our research system kind of daily into in a pilot, and now they're trying to scale this to the whole health system. So very exciting. But what I want to highlight is that after you do clinical trial matching, right? You can actually turn this into a hypothesis generation and testing engine, right? Because you can conjure up the training, the virtual cos arm, the case arm, and virtual control arm, right? So here we did a tiny bit of baby step with Providence collaborators, right? For example, this is the highlighted is the original Keytruda trial, right? So we show that with the real world data, we can actually generate virtual trial, and then we can get actually the virtual hazard ratio, which is what you're looking for in the trial, right? That are quite comparable to the published hazard ratio, right? So in the interest of time, I will basically just mention that here's a real world patient journey. Obviously, they identify the dates and everything. But you can see at the beginning, within 2 months, 2 weeks, the patient have CT, PET, test ray, MRIs, and so forth, right? And then the patient start undergoing treatment, right? Everything looks good for until 8 months later, the patient doesn't feel well. Then they find out, oh, actually the cancer have relapsed, right, and metastasized. And then within a month, the patient died, right? So it's a very sort of sad story. Unfortunately, it happened all over the map, right? So and the question is that can we do much better, right? So with the multimodal longitudinal modeling, right? We can argue that we are already doing very well on the left-hand side, right? So we can already help patient, human expert to do something that they are already good at, but just take away the chores and so forth. But can we also start to figure out things that even the best doctor cannot do today, right? To automate discovery, invent new guidelines, and so forth. So thanks very much. I want to highlight my team who did all this great work, and also obviously all our collaborators without whom we can't do anything. Thanks.
Great, great. Thanks, Hoifung, for the fantastic talk. We only have a couple minutes. There's one question in the chat about privacy and on the
Mm-hmm.
patient multimodal patient data. Maybe you
Mm-hmm.
can talk about the clearly you have thought a lot about this, both from
Yeah.
training and the inference stage and how those
Yeah.
sensitive data is. Yeah.
Yeah. Absolutely. That's really the first big question that we have to be super careful about the privacy and the compliance, right? So one thing I want to first highlight is that all our research involving actual patient data, all of them are sitting in our collaborators tenant, right? So in their private tenant, and then we follow all the guidelines and IRBs and everything to credential a very small selected folks in my team to get into their environment, and then we conduct all the research within that environment, right? So that's really sort of the very safe way to make sure that everything, all the guidelines are here. And so yeah, so absolutely that's really the foundation. And also another thing I want to highlight is that obviously the most important thing is to improve patient care, right? So that's really the ultimate objective, and everything we are doing try to be in service of that.
So there's a couple of new questions. So digital twins can be used for training biomedical foundation model. What could be a good way to validate the causality effect?
Uh-huh.
Those,
Yes, yeah, yes. So this is really the holy grail, right? So one of there is a reason why the gold standard for medicine is randomized control trial, right? I mean, Jimeng, you did so many amazing research there. Um, the reason is because of the causality versus correlation, right? So randomization is a very effective way to counter that. When you go to the real world observational data, you lose that, right? So there are some kind of like pretty kind of basic things that we can piggyback on some of the kind of like progress in the causal reasoning community, right? So when we did this simulation study, right? So we basically using obviously some of the very standard way like propensity matchings and so forth. You want to make sure the distribution in the virtual case arm and the virtual control arm are as similar as possible, right? So that you don't introduce accidental confounders to make the differences. But that there is no guarantee about you actually eliminate all those things. So you can think about this as mostly just a hypothesis generation way, right? You can also very quickly start to get some signal, but you can't guarantee that everything is really buttoned up, right? So most likely we still need some sort of randomization in clinical trial, but hopefully this can drastically cut down how many patients you need to enroll, right? So and also accelerate the process.
so here, if I can ask a follow-up question on this,
Yeah,
if you do you simulate both the control and treatment arms or just the control arm? What if the treatment arm is a new drugs, right? Then there's no.
absolutely. So here we are looking into the marquee cancer drugs, right? So and most of them is because a drug has already been used, right? So exactly like I said, like if it's a new drug, obviously in real world data don't have. So actually, the most fruitful direction is actually what you alluded to, is to basically build a control arm, right? So the control arm you can expect always exists because by definition, control arm usually are just a standard of care, right? So usually you have those data there is one big bottleneck in our experience is that the trial often have much higher detail healthcare quality compared to the general real world setting, unfortunately, right? So what we often find is that the control arm, you may be artificially inflated the difference from a real treatment arm. So when we basically get virtual treatment arm and virtual control arm from the real world data, those effect cancel out, right? But when you compare the real treatment arm with external control arm, that is one of the biggest bottleneck that we observe, and we don't have perfect answer for that yet. And in fact, that's currently one of the big bottleneck why FDA doesn't fully trust this, except for rare disease, right? So, but I'm hopeful that like collectively we might be able to figure out ways to deal with abstract away that factor, then we can make control arm basically universal for all the trials.
Yeah, makes sense. I know we
Mhm.
run out of time. There's still some questions. I mean,
Mhm.
if you have to join another meeting, we can end here or
Mhm.
take a couple more questions. We can stay a few more minutes.
Yeah. Yeah, I have a few more minutes if so I can quickly answer. Maybe the next question is like Hanying, right? So end-to-end pre-training for multimodal compared approach to focusing. Oh yeah. This is a great question. So um I I guess what you're asking is really like early fusion versus late fusion, right? So For example, if you look at like Gemini, you look at maybe Meta's Tremorons and so forth, they feature something they will brand it as early fusion, which means that you assume your training data is interleaving, right, multimodal data, right? In fact, they use a single vocabulary, which they partition into different modality, right? So they still have partition of different modality, but they actually have a single vocabulary, and then the training objective just become mostly just predict next token, right? So that's obviously a very exciting paradigm to an alternative hypothesis than what we're trying to do, right? So our hypothesis is that if you have lots and lots of those interleaving data, right, then which actually happen to be the case for a lot of the web multimodal, which are like web images, right? HTML, you have images, you have maybe even video, you have text, and so forth, right? So in that case, the interleaving part can actually give you a unified way to generate, learn, but also capture a lot of those kind of like, spatial and temporal, kind of sequential kind of interdependencies. Um, on the other hand, if you don't have a whole lot of those kind of interleaving things, then the late fusion could have advantage, right? So because you first do a lot of those pre-training on individual modality by using a lot of those unannotated individual modality, right? So usually those kind of data are a lot more than the interleaving pairwise or temporal data. So I think this is the jury is still out. And I wouldn't be surprised if in the future someone figure out, hey, there are sufficient in the living patient journey that you can just do an early fusion, right? My observation is that even in the approach when people talk about early fusion, there was still some specialized processing that actually reminiscent of the late fusion. For example, they don't literally generate pixel by pixel for image, right? They reserve, for example, the whole image and say, oh, next I need to generate this image. So and then the vocabulary right now is also completely separate, right? So it's a little bit different than multimodal where they literally mingle all the languages vocabulary together. Today, as far as I know, their vocabulary, actually they still separate, here's the image vocabulary, here's a speech vocabulary, here's a text, and so forth. So I would say this is a very exciting frontier that I don't know the answer, and we are betting on the late fusion, at least for now. But we are scientists, right? So if we see evidence that early fusion better, then we'll switch.
Well, I think this is perfect time, probably. Let's thanks the speaker one more time. Thanks, Hoifung, for the fantastic talk and deeper insight for the question answer. Thanks for everyone joining this webinar, and we'll stop here. Thanks.
Thanks so much, Simon. Thanks,
Bye.
everyone. Bye.
Thank you. Bye.